Swayam Prabha. Digital India. Educated India.
So now, if we plot if we plot this prototype function, then it looks something like this. So this graph shows the Chebyshev polynomial, Chebyshev prototype function, that is the gamma n value, not just the Chebyshev polynomials, but the various orders like n equal to 1, 2, 3, and 4. Now what you see here is that, say if we consider the first order, this red line, then this is very similar to the first order for a maximally flat prototype function. But note what happens when n equal to 2, n equal to 3, and n equal to 4. So for n equal to 2, we have a single ripple, this blue line. For n equal to 3, we have 2 ripples, black line. N equal to 4, we have 3 ripples. These prototype functions are also known as equal ripple prototype functions, because you see these ripples, even though they are present, wherever there is more than one ripple, these ripples are of equal height. Okay, so that's why these Chebyshev transformers are also called equal ripple transformers. Now the question is, how do we design the transformer? So we have found an expression for the prototype function, but we still have not found a relationship between the gamma k's for a multi-section transformer and this prototype function. Okay, so let us go back to our design. So recall that the input reflection coefficient of an n section transformer gamma in theta is given by this equation, right? And for convenience, we take gamma k as equal to half of ln z a plus 1 upon zk. Now, on the other hand, we also have our gamma in theta, which is this equation. I'm just rewriting that equation. Let me write it in terms of E. Right? Now here I have to obtain the expression for this theta m of this prototype function first. So an alternate way of expressing this Tn x, that is the Chebyshev polynomial, is like this. And this is another alternate way of expressing the Chebyshev prototype function. So now here, instead of say x, if we substitute, instead of x, if we substitute sec theta m, then the expression we get is this. Okay. Now coming back to this equation, from here we can write this gamma m, which is equal to modulus of gamma in at theta equal to theta m is equal to gamma L times Tn sec theta m, gamma and magnitude in the numerator. So then now the value of this Tn sec theta m we have just determined in this equation. Okay. Now substituting it, so we can write Tn of Tn gamma m is equal to mod gamma L upon cos h of n cos h inverse sec theta n. Okay, and then so from here we can try to find out the value of sec theta n. So we can write cos h n cos h inverse sec theta n is equal to modulus of gamma m on gamma m, which in turn implies n cos h inverse sec theta m is equal to cos h inverse mod gamma L upon gamma m, on which we can write sec theta m is equal to cos h of 1 upon n cos h inverse mod gamma L upon gamma m. Okay, and this in turn can be further simplified as cos h of 1 by n cos h inverse so this is the value of theta m. So see, if we know the order of the Chebyshev polynomial, if we know the value of gamma n, if we know what is the load, what is the characteristic impedance, then we can find out theta m, this quantity, from this equation. And once we know the value of theta m, we can find out the fractional bandwidth delta f upon f0, which is given by this equation. Okay, so this is how we can find out what is the fractional bandwidth for a particular order of a Chebyshev prototype function when the other values like RL, Z0 and gamma m are given. So now you may ask, how do I find out whether particular filter order, a particular order of the matching network, or rather how do I find out the order of the filter that would be most appropriate? So the way to do it is, suppose you have been given a particular value of gamma m that has to be achieved. You know what is RL, you know what is Z0. Then you first take n equal to 1 and see what is the value of theta m, and then find out this delta f upon f0 and see whether that is satisfying your bandwidth requirement. If not, then you increase n to 2, then again find out delta f, then again find out theta m, again find out delta f upon f0. This way, go on increasing the value of n till you get to a point where your fractional bandwidth obtained is either equal or more than what you need. It should be more than what you need. So that particular value for which either the fractional bandwidth is equal or more for a particular value, that value of n is the required order of your multi-section, is the required order of your prototype function. Okay, and as usual the order corresponds to the number of sections that are needed in the multi-section transformer. Okay, so we obtained the value expression for the fractional bandwidth. The next step that is left is how to find out the values of the z's of the multi-section transformer. So let us go back to these equations. Okay. We have these equations. Now let us consider, let us show this by an example. Let's say n equal to 3, okay, and say n equal to 4. Then this Chebyshev prototype function for these two cases, that is n equal to 3 and n equal to 4, will be given like this. So these are quite long expressions. Okay. The second point is, let us try to simplify this expression for a symmetric case. So first thing that we did is we found out the expression for this T3. Okay, so we are going to equate these two equations and then find out the values of gamma k based on the values in this equation. Let us now take, say, n equal to 3. So for n equal to 3, we have the Chebyshev polynomial like this. Further, for n equal to 3, this gamma in from this equation, we will get k here. Okay. Now suppose we assume that the multi-section transformer is symmetric, that is gamma 1 is equal to gamma 2 and gamma 0 is equal to gamma 3. Then what do we have? How can we simplify this equation? Then in that case we can write this as which can be simplified as okay. So this is the value of gamma in from the multi-section transformer theory, and the value of gamma in from the Chebyshev prototype function is this one. So let me now write both the equations together so that it becomes clear. So here n is equal to 3, then this becomes equal to I'm using this equation. This equation. And if I then equate with this equation, then I will get here this n is equal to 3. Get here okay. So now comparing these two equations, this one and this one, what do we see? We see that, let's see the coefficient of cos 3 theta here and the coefficient of cos 3 theta here. Then we can write that gamma 0 is equal to 2 gamma 0 is equal to a sec cube theta m. Okay. So from here this implies gamma 0 is equal to half a sec cube theta m, and this must be equal to gamma 3. Similarly, comparing the coefficients of cos theta, this one, and this one, we see that 2 gamma 1 is equal to a times three sec cube theta m minus 3 sec theta m. From here, then gamma 1 is equal to 3 by 2 a sec cube theta m minus sec theta m, and this is equal to gamma 1. Okay, and then we know that gamma k is equal to half ln z k plus 1 upon zk. This simplification is taken once again for getting consistent solutions. So here now you substitute the values of these gamma zeros, gamma 1, this gamma 0, gamma 1, and then using this equation you can find out the values of z1, z2 and z3. In your notes I have given a problem. Please try to go through it and see how it is solved. Finally, I would like to show that plot that I showed for the binomial uh, prototype function also, where we compare the equation of the prototype function with the actual input reflection coefficient obtained from ADS. So see this graph shows the plot of the exact Chebyshev equation, this black one. So this is the gamma n plotted from the Chebyshev prototype function, and this red curve shows the plot that has been obtained by solving for the various z's of the of this three section Chebyshev prototype of this three section Chebyshev matching network, and this red line has been obtained from ADS, whereas this black line has been obtained from the exact equation. As you can see, there is again a small discrepancy, and this discrepancy is because of that simplification for gamma k that we take, where we take gamma k is equal to half ln of zk plus 1 over zk. All right, so with that we come to an end to this lecture 11. In the next lecture, we will be starting with microwave components, starting with one port devices. Thank you.